and hello, and welcome to this multi-part series. Welcome to the last part of the multi-part series, um, focusing on the 2017 chemistry paper, um, DBE chemistry paper, November 2017. We've tackled a lot of questions up till now. Finally, we are down to our last two questions. Question 9, which is on the electrolytic cell. Um, and question 10, which is on processes, industrial processes. Okay, so question 9, simplified diagram below represents an EC cell used in the refining of copper. Now, we refine copper, um, very simple reason. Copper is very valuable to us. Um, Sorry, I lost connection for a bit over there, but like I said, we refine copper as it is very important to us, and is very important in the usage of electrical wiring, and it goes without saying that's one of the most important things within society, as it allows us to transfer or transport electricity. And the problem with unrefined copper is it's very, you would think very pure at 99%, but we refine it to about 99.95% just to ensure that the quality of the electrical wires that we use is very, very, very reliable. Okay, because small concentrations of impurities will noticeably lower the conductivity of copper, and we don't want that. We want it to be at performing at optimum level, so we increase the purity from 99% to about 99.5. Sometimes higher, sometimes just a little bit lower, but around that ballpark. Okay, cool. Let's carry on with let us carry on with question 9. Now they say what type of power source, AC or DC, is used to drive the reaction in this cell? Well, in this specific example, we are looking at let's see, we are looking at the power source rated CUCR. Um, Okay, in this case, we are using direct current to drive the reaction in the cell, and that is a standard of EC cells. We're using direct current. Then, when an electric current passes through the copper chlorine solution, the mass of the electrode will increase. Then they say, is electrode P the cathode or the anode? Write down the relevant half reaction to support the answer. This is the cathode. Okay. And the reason why is, or the equation that you would use to show this is the half reaction of copper. Yeah, copper being the cathode, we will, let me add this as a formula. There would be your formula to motivate your answer, showing that copper in this case is being reduced in order to, or copper ions are being reduced to form pure copper. Okay, then they say the impure copper contains zinc impurities which are oxidized to zinc ions. Okay, refer to the relative strengths of the oxidizing agents to explain why zinc ions will not influence the quality of pure copper produced in this cell. Well, very simply, the copper ions are a stronger oxidizing agent than the zinc ions, and so therefore the zinc ions will not be reduced to zinc, and instead the copper ions will be reduced to copper. Basically, this will occur as opposed to zinc ions becoming the copper in this case. Okay, then 9.4. The two electrodes are now replaced by carbon electrodes. First of all, what will be observed at electrode Q? Let's just check. Electrode Q would be the zinc. And over there, oh, they are replaced by carbon electrodes. Okay. All we observed electrode Q. Well, in this case, given that we would have carbon electrodes, again, the copper would be reduced. No, in actual fact, in this case, the chlorine would form, and what would happen is the chlorine would form in gaseous form, and not only that, it would start to bubble at electrode Q. So the chlorine would form from chlorine gas and would be bubbled at electrode Q. Then, how will the concentration of the electrolytes change as the reaction proceeds? Choose from increases, decreases, or remains the same. The concentration of the electrolyte. Oh, okay. Once the concentration or once the reaction happens, well, the concentration of the electrolyte would decrease as less and less of it would be present due to the formation of chlorine at electrode Q, as well as the rest of the reaction occurring. And so therefore, it would decrease. And that would be it for question 9. Question 10. Now, like I said, question 10 processes and are normally the last question of the paper. So after this, we will have no other questions to do and we'll be done with the 2017 paper. Okay, let's tackle it. They say the equations below represent two industrial processes involved in the preparation of ammonium nitrate. Process X, vanadium pentoxide. Okay. Process Y, referred to as the Haber process. Okay. Before they even asked them, process X is known as the Ostwald process. Process Y, using nitrogen and hydrogen very high temperatures with a lot more steps than what they're showing, is used to form ammonium nitrate and is referred to as the Haber process. After Fritz Haber, the Ostwald process is on the left. Okay, then most of these questions are just questions you should basically have studied beforehand to know the answers for. Let us tackle them. Write down the name of substance A. Substance A is ammonia. Yes, ammonia is used to form ammonium nitrate. Okay, ammonia 4A. Then the formula of substance B. Let's just have a look. 2NO plus O2. It is a oxidation reaction. And what is then formed is that guy right there. Yeah, nitrous oxide. Then the name given for reaction I. Okay, once again, this is just theory work. And it is the catalytic oxidation of ammonia. Then the name of the name or the formula of the catalyst used in reaction one. I think I might have already given that away, but it is platinum. PT platinum. Versus X and Y, I've already given the words. Okay, very famous processes in their own right. Okay, now they want the balanced equation for the preparation of ammonium nitrate from the products obtained in process X and in process Y. Just one more time. Balanced equation for the preparation of ammonium nitrate from the products obtained in process X and process Y. Okay. And for that one, start off with ammonia with the 3 lines from A, giving you NH3. That is added to HNO3, okay, nitric acid. And what you get as a result is what we're looking for, NH4 NO. Let's just try that again. NH4 NO3. That right there is balanced. Yeah. 10.2. A 15 kg bag of fertilizer contains 5% phosphorus, 10% nitrogen, and 15% potassium. Okay. Calculate the mass of phosphorus in the bag. Well, this is now just formula work. We are looking for the empirical formula of all of these. So N is to P is to K as a ratio is this. Okay. And so therefore, in this case, this is 10. This one is going to be 5. It's given to us as well. And this one is going to be 15. Okay. And if what I'm doing right now does not make sense, I might need to go back and have a look at your notes again as to how to work with fertilizers. Okay. Then from there, the mass of the fertilizer is given as 30% multiplied by that 15 that we're looking at. Let's just put this over here. Okay, it's a 15 kg bag, and the phosphorus makes up um, that much of what we're looking at. Okay, altogether, these organic products are 30% of that 15 kg. So hence we start off with 30% of 15. And once we get that, which is equal to, let's see, 3, 15 is equal to 4.5 kg. Yeah. To 4.5 kg. And now if we move on to the mass of phosphorus, we are looking at 5 out of 30, 5 parts from that 30% of 4.5 kg. I mean, simply finding the parts of a whole, and that is equal to 0.75 kg. Okay, here we go. 0.5 kg, and that was 10.2.1. Now, 10.2.2 mass of the filler in the bag. We'd already found that the percentage of be 30%. So the percentage of filler is equal to, therefore, 70%. And well, 70%, 0.7 times that 15 kg that we started with, which is equal to 10.5 kilograms. Yeah, hopefully you can see it now. And that is the end of the 2017 question paper. Hopefully this has been a great help, and I shall see you very soon in order to tackle some more papers like this, as well as a bit of math. Take care. See you in the next.